So this is your third and final short video to watch dealing with stoichiometry, specifically limiting reactant, excess reactant, percent yield, and percent purity. If you've not watched the other two videos, the two from YouTube, the one on limiting reactant and the one on percent purity, you should stop now, go back and watch those first because that's going to give you the basic information. And now I'm going to work 3 different problems for you, showing you each time how to do limiting reactant, excess reactant, percent yield, or percent purity. Our first problem here, we want to be able to find out the limiting reactant and the excess reactant, as well solve for the theoretical yield, and then this is something new that we didn't do in first year chemistry. We actually want to find out how much excess reactant do we have, how much extra. Now every stoichiometry problem has to start with a balanced equation. In this case we have ammonia plus our copper 2 oxide gives us the desired nitrogen gas, copper, and water. And do a quick balance on this. And then I like to set up my given and find underneath. We know we have 18.1 grams of ammonia to start with, 90.4 grams of copper oxide. And we want to find out what the theoretical yield of nitrogen is. Anytime it mentions theoretical yield, that means if this experiment was run perfectly, how much nitrogen could we really produce? So we're going to try and find the grams of nitrogen, and that's going to be our theoretical yield. Our other things are copper and water are just along to balance the equation. One of the ways that you know you're always dealing with a limiting reactant problem is you always have data about all of your reactants. And notice here we have data about our ammonia and we have data about our copper 2 oxide. Because we have 2 pieces of data, that means we have twice the fun. We need to do 2 problems. These are just like the stoichiometry problems we did the other day in class. 18.1 grams of ammonia, and we know grams is pretty much useless to us. We always need to change that into moles first. Grams of ammonia on the bottom, 1 mole of ammonia at top. I'm not going to write out the molar mass problems, but I do want you to be extremely careful. The molar mass of ammonia is 17.04. Notice that this first step here, the only number I can put in front of moles is a 1. Now the next step is our mole ratio step, and that's where we use the coefficients from the balanced equation. So our grams cancel, so now we know that moles of ammonia needs to come down, and moles of what we want to find goes on top. Looking at our balanced equation, we see that there is 1 mole of nitrogen, 2 moles of ammonia. That cancels out our moles of ammonia. Now our last step is we want to get this back into grams. So 1 mole of nitrogen again, and the molar mass of nitrogen is 28.02 grams. And our moles of nitrogen here cancel out. Now notice the only step where I put in numbers other than 1, where I use the balanced equation, is here in my mole ratio step. We'll go ahead, let's label that so we remember that's our mole ratio step. And at that step, we can put any number in front of moles that we want to. It's just based on the balanced equation. So 18.1 divided by 17.04 divided by 2 multiplied by 28.02 gives us 14.9 grams of nitrogen. Now we're not going to circle that yet as being our right answer because we're only halfway through this problem. We now need to go and take our other reactant, our copper oxide, and see how much nitrogen it could produce. So the steps will be the same. Taking our grams of copper oxide And first, changing that into moles. Notice I'm keeping my 1 in front of copper oxide at this step, and the molar mass is 79.55. I'm going to cancel those units out. After I've got my grams turned into moles, my next step is always my mole ratio. This time I want to bring moles of copper oxide to the bottom to cancel. Moles of nitrogen on top, and once again I'm at my mole ratio step again, so I want to have 1 mole of nitrogen for my balanced equation, and this time I'll be using the 3 moles of copper oxide, sorry. Cancel out my copper oxide, and you'll notice here this last step's going to be the same. We want to convert our moles of nitrogen into our grams of nitrogen. Moles of nitrogen cancel. Go ahead and do our math. While you're doing your math, I'm going to circle so we make sure that's our mole ratio step again. And when we come up with our answer, we get 10.6 grams of nitrogen. Well, the theoretical yield is always based off of the limiting reactant, that thing you run out of first. Well, in this case, the way you find the correct answer is whichever one's smaller, 14.9 or 10.6. Well, our 10.6 is our smallest, so that's our theoretical yield. It's kind of weird because it's the smaller number, but it's the maximum amount that we can make based on our limiting reactant, which in this case is our copper oxide. It's really important to mark the copper oxide at this step because that's going to be critical as we move through the problem. So our first step is done. We have found our theoretical yield. We know what our limiting reactant is, and in fact we also know which reactant we have excess of, our ammonia. But now what we want to do is figure out, well, how much excess do we actually have? How much extra ammonia is really present? So to figure out how much excess there is, we're going to take the amount that we have, we're going to subtract how much we used in the reaction, and that'll tell us how much excess we have. Well, we already know how much we have because that was given to us at the beginning. We know we're starting with 18.1 grams, but what we need to do is figure out, well, how much did we actually use? Well, that's going to be based on the limiting reactant. That's why it's so important to find at the beginning because everything else works off that limiting reactant. So if we have 90.4 grams of copper oxide, let's use stoichiometry again to figure out, well, exactly how much ammonia do we need to react with that? Just like before, change our grams into moles. This time the mole ratio is going to be a little bit different because now we're not solving for a product this time. We want to see how much of that other reactant we used. We'll still cancel out our moles of copper oxide on the bottom. We'll have our moles of ammonia on top. And still going back to that balanced equation, there's a ratio of 2 to 3, so we're still doing stoichiometry. We're still using our balanced equation in there. And now let's turn that back into grams. This step gets a little bit easier because you've already calculated all those molar masses already. So we will now be careful here because you're going to divide by the 79.55. At this next step with the mole ratio, you can then multiply by 2 and divide by 3. Make sure you do both of those steps. And then multiply by your 17.04. And what we find is 12.9 grams of ammonia was used. So up here, minus our 12.9 grams we used. We subtract that and we find out we have 5.2 grams of ammonia in excess. So there we found our theoretical yield based off of our limiting reactant, and then once again we used our limiting reactant in order to determine how much excess reactant we had left. So this should be pretty standard up to the how much excess do we actually have. Our second problem I have for you is stoichiometry and percent yield. And this one, I think I'm actually going to leave for you to do your own calculation. I'm going to pop in the answers in here so that you can pop in the answers in on Edpuzzle so you can check yourself. But I think you can actually do this one. I'm just going to give you a little information right here about how to do the percent yield. Now, I will warn you, I've put some strange units in here. That kilogram and kilogram. You can't use kilograms. You got to make that grams first. So maybe just a little help here to get you started. We'll double check the balanced equation. I'm using methanol, the simplest alcohol. It's a pretty easy one to balance. It just needs a 2 in front of the hydrogen. And be careful. You have 68.5 kilograms, which is the same thing as 68,500 grams. And you have 8.6 kilograms, which is the same thing as 8,600 grams. We want to calculate the theoretical yield of methanol. But we also want to know what's our excess reactant and how much do we have, and what's our limiting reactant. That part of the problem is exactly like what you did before, what I just showed you. So you can practice that part on your own. What I want to add here and talk to you a little bit about is the percent yield. We did do this last year, and you probably will remember a good bit of this. The formula for percent yield, and this is telling you how well did you do actually producing what you said you're going to produce. So we know we can figure out how much we're theoretically supposed to make based on the balanced equation. And then we go and actually do the experiment and we produce some amount of methanol. Well, that amount that we produce is known as the actual yield. And you'll notice that that will always need to be given to you in the problem. They'll have to tell you how much you actually produced. Percent yield, you compare the actual to the theoretical, multiply by 100, and that gives you a percent yield. Now I will tell you, you'd like your percent yields to be closer to 100%. You want to make as much as you possibly can. And you like, in contrast to your percent error, where you typically want it as close to 0 as possible. So I will post these answers up on Edpuzzle. So after you work this one, you can plug your answers in and check to see how you were doing with this. Let's be careful. Let's make sure let's try and keep our answers to 2 significant figures. That way it'll match up well and you'll know if you're getting them right or not. One other thing I want to show you that you can do with stoichiometry, and something we haven't talked about before, is percent purity. In this case, we have an impure sample of sodium sulfate, meaning the sodium sulfate's there that we're really concerned about, but there's some other junk in there that we don't really want. So we want to figure out, well, how pure is our sample? And so what we're going to do is we're going to take that sample, we are going to dissolve it in water and allow it to react with barium chloride. Actually, what we're setting up here is a metathesis reaction. Sodium sulfate, barium chloride. Let's finish this off before we look at the rest of the problem. Remember, metathesis, we're switching the anions, so sodium's going to go be with chlorine and barium is going to go be with sulfate. So we end up with barium sulfate and sodium chloride. Now, one of these things is a precipitate. And we're not making you memorize the solubility rules. What we want you to be able to do is look at the charges on those and see which of those things is more likely to stick together and not dissolve. Well, this one's a little bit easy because we know a lot about table salt. Table salt dissolves, and notice it's only got a +1, -1 charge difference. That's a smaller charge difference in comparison to our +2, -2. So in this case, that bigger charge difference makes the barium sulfate our solid. A little bit of balancing here with a 2 in front of the sodium chloride. And we have 1.89 grams of impure sodium sulfate. So it's not 1.89 grams of sodium sulfate, it's 1.89 grams of some sodium sulfate and something else is present. But we know when we do this reaction that we absolutely come up with 1.75 grams of barium sulfate. Well, if we know how much barium sulfate we can make, we can work our way back and actually figure out how much sodium sulfate would be present in its pure form, because the impurities that are in there aren't going to make barium sulfate. We'll be able to exclude them. So this just becomes another stoichiometry problem, although this time it's not limiting reactant because we only have one thing we're working with, and we're actually working from a product back to figuring out how much reactant. So 1.75 grams of barium sulfate. Go ahead and change that into moles. Molar mass of barium sulfate is 233.39. Using our mole ratio again, this time though it is a mole ratio of 1 to 1. But every time you have a balanced equation, you can be pretty sure that you're going to have to do mole ratio somewhere. So we've got grams canceled, moles canceled, and one final step, turn it back into grams. The molar mass of sodium sulfate is 142.04 grams. And we'll put our 1 mole on the bottom. So we know we made 1.75 grams of barium sulfate. The only place the sulfate can come from is from our pure sodium sulfate. So we're going to work back and figure out how much sodium sulfate we have there. And we've got 1.06 grams of sodium sulfate. That is pure. So look at the difference between our pure value and our impure value. There was a lot of junk in that sample. Well, we can calculate the percent purity by comparing our pure to our impure, very similar to doing a percent yield problem. We take the pure amount, divide it by the impure amount, times 100, and that'll give us our percent purity. So we have 1.06 grams, that is pure, over 1.89 grams, that is impure. Whoops. And our purity of our sample is only 56.1%. Not very pure at all. So after watching your Edpuzzle video, you should come to class, next class period, ready to actually work some problems in class and get some help from me and work in small groups. I'll see you next time.